Hello everybody. Today we start lecture 21, and it will be section firstly differentiation, of an inverse function. So the main result here is the following theorem. If f from x to r is strictly monotone on an interval x, and is differentiable on x, then the inverse function f minus 1 from f of x to r is differentiable at y naught equals to f of x naught for any x naught in x such that f prime at x naught is not equal to 0. Moreover, f minus 1 prime at y naught equals to 1 over f prime at x naught. That is the relation between derivatives of the function and its inverse. Oops, I wonder if there is somebody in the audience. Yeah, there is at least one, yeah, because otherwise I was afraid. No audience. It's good. Okay. Proof. F is differentiable on x, hence f is continuous. We proved it during last lecture on x. Then, by the theorem, the inverse function Okay, inverse function theorem will be later in a different sense. Inverse function theorem, which was before, I mean, later it will be different version. F minus 1 is continuous on f of x, and f of x is an interval. Okay, so there is first condition, if in particular if x is an interval, open interval, then f of x is open interval as well. So it means that the condition for differentiability, namely the domain should be an open set, is satisfied. Okay, so now we should prove the differentiability, and for that reason we need to consider the following limit and to check if this limit exists. So we need to check if the following limit exists according to the definition. That is what we want to check. But we can observe that from the definition of an inverse function, what we know. So we have the following correspondence. There is an interval around x0, and the function f maps that interval onto an interval around y0 in one-to-one manner. So it means for every point here, f gives precisely one point there and vice versa. So we have also the inverse function which maps this interval back. And it means that moreover, because of continuity of the inverse function, once y tends to y0, it's equivalent to say that x tends to x0, where x is f of y. So we can rewrite this limit as x tends to x0. The restriction to take limit of composition is fulfilled because of strict monotonicity. So we have one-to-one correspondence. It means f of y is never equals to y0 once y is not equals to y0. So we can write here in notations of the direct function like that, and that is 1 over limit as x tends to x0 f of x minus f of x0 x minus x0 1 over f prime at x0. once again, this equality is conditional. So at the moment when we write it, it might be not correct, but we know that this limit exists. It is equal to this derivative, and the derivative is not zero by the supposition. So it means that in fact the equality is correct, since we checked that the limit exists and it is not equal to zero. So it's okay. And that's all. We have proved the theorem. Okay. That is very, in fact there is a remark, maybe it's useful remark. So remark, under the supposition of differentiability of f minus 1. The equality for its derivative can be proved by, so what we know, let's say f minus 1 of f prime at x naught equals to f minus 1 at f of an x naught times f minus 1 prime times f prime at x naught. That is by derivative by the chain rule, right? And that is f minus 1 prime at y naught times f prime at x naught. And from the other side, f minus 1 f of x is identically x. And derivative of x is 1. Hence, this should be 1. And it gives us same equality for the derivative, right? But you see that no way to prove that the inverse function is differentiable in this way. So you should suppose in advance that the function is differentiable. Okay, now we are able to proceed to the main topic of today's lecture, and that is section 21.2, table of derivatives. At the moment we know the first line of the table, the derivative of x to the power n equals to n times x to the power n minus 1. Nothing else yet. Okay, now let us consider a little bit more, right? For example, let's start with very simple limit 1/2 square root of x. Here we should suppose x is positive. strictly positive. And we refer to the proof of that equality, we refer to our theorem. So I will keep the theorem and we proceed by using that equality. So square root of x, so y is square root of x is equivalent to x equals to y squared for x is positive, right? So it means that square root of x is inverse to the function y squared, right? So maybe I'll change letters now, right? So x equals to square root of y is x squared minus 1, right? That is the inverse to the function y equals to x squared. Yeah. So the derivative by the equality is 1 over x squared prime, 1 over 2x. And what is x? X equals to square root of y, and it gives us 2 square root of y. And that is precisely the equality from the table, right? And that is how it works. Okay, next line is about exponential functions. So let us consider e to the power x. Let me write it here. E to the power x prime equals to e to the power x. Here, no restrictions for arbitrary x. Okay, e to the power x prime, let us compute it at a point x naught. By the definition of the derivative, that is limit x tends to x naught, e to the power x minus e to the power x naught over x minus x naught. We can write it like limit x tends to x naught, take e to the power x naught as a common multiplier, and then here we have e to the power x minus x naught minus 1 over x minus x naught. And if we'll denote x minus x naught as a t, then we can write as t tends to 0, e to the power t minus 1 over t, and that is e to the power x naught by a version of the second remarkable limit. There is a version of second remarkable limit which says this limit is 1. That is 1. That is how we check the equality 3. And then immediately we can check the derivative of logarithmic function, because y equals to logarithm x is equivalent to x equals to e to the power y for x positive. So again, we can write in a different notations, that logarithm y is e to the power x inverse function. Here minus 1 is just the inverse, not 1 over. So by the inverse function theorem, the derivative is 1 over e to the power x prime, that is 1 over e to the power x, and e to the power x, if x equals to logarithm y, is just 1. That is how we prove the equality form. Slightly more general, equalities are about the derivative of general exponential function, and that is a to the power x logarithm a for a positive. And here, how we can proceed for the proof of that line. A to the power x prime is, if we'll rewrite as e to the power x logarithm a, then we can use the chain rule. So we take exponent of x to times logarithm a. So it means we have the derivative of exponent, and the derivative of exponent is the exponent itself, times x logarithm a prime, and here we have a constant multiplier, so just the multiplier remains, and e to the power x logarithm a is a to the power x. That is, it gives the equality. For the general logarithmic function, we have the following. Again, x positive, a positive, and a not equals to 1, otherwise we cannot define logarithm. So, but here we can proceed in an easier way because of equality for logarithms, which is well known, like that, right? And then we refer to the fourth equality. Now we can generalize the first and second. So general power function is ax to the power a minus 1. Here x is positive and a is now arbitrary real number. Now how we can proceed here? X to the power a. We can write it like e to the power a logarithm x, and again by the chain rule, the exponential function gives itself times a logarithm x prime, that is e to the power a logarithm x times a over x, and e to the power a logarithm x, x to the power a, and here we have x to the power a minus 1, so what we wanted, right? That is how general power function is differentiated. Now we can proceed with trigonometric functions. Okay, so okay, I'll write firstly here. It's sine x prime is cosine x. Here, no restrictions. So, how we proceed? Sine x prime at x naught, let's say, that is by the definition is limit x tends to x naught sine x minus sine x naught over x minus x naught. We can write it using trigonometric formulas like 2 sine x minus x naught over 2 times cosine x plus x naught over 2 over x minus x naught, and that is limit as x tends to x naught sine x minus x naught over 2 x minus x naught over 2 times limit cosine x plus x naught over 2. That is a conditional equality. Again, we don't know yet precisely if it is correct or not, but it is correct. Why? Because both limits exist and are finite. The first one, you see, x minus x naught over 2 tends to 0, and we have the first remarkable limit, that is 1. And the second, we know that trigonometric functions are continuous on their domains, so cosine is continuous. Hence, if x tends to x naught, its argument tends to x naught as well, so we have the limit is cosine x naught. And it gives us precisely the 8th line. Okay, 9. Next is cosine. The proof is quite, in fact, there are, sorry, minus, I forget minus. We can proceed by either by the same, or we may use trigonometric formulas again, and another type of trigonometric formulas and chain rule. So I'll proceed like that. So cosine x prime, cosine x is sine pi over 2 minus x. And then by the chain rule, derivative of sine is cosine times pi over 2 minus x prime. Derivative of pi over 2 minus x is minus 1, so we have minus, and here we have sine. That is how we may proceed here. Next, tan x 1 over cosine squared x, or secant squared x prime. Here, of course, we should put a restriction: x not equals to pi over 2 plus pi k natural. So x should be in the domain of tan. For that reason, we just use the rule for derivative of a ratio, right? So we have derivative of numerator times denominator minus derivative of denominator times numerator over square of the denominator. Then we use former formulas. So we have cosine squared x plus sine squared x, and it gives what we want. 11th, cotan prime is minus 1 over sine squared x, or minus cosecants, in fact, cosecant squared x. Again, there are, I forget to put restrictions here, x not equals to pi n. Oh, sorry, integer, not natural, right? N integer, yeah. So, for cotan, again, we may proceed using similar representation, that is tan of pi over 2 minus x, and that is 1 over cosine squared pi over 2 minus x times pi over 2 minus x prime, and that is minus 1 over sine squared x. Okay. Yeah, that is about trigonometric functions. Now inverse trigonometric functions, and I should explain my position. In your textbook, inverse trigonometric functions are denoted in a traditional manner, more traditional manner. In fact, I prefer same notation as in your lecture notes. But I worked for many years in Istanbul, and we used another textbook by Thomas, University Calculus. But I don't recommend it as a, yeah, so it's just to show that in many countries there are different notations, so you should know both of them. And in that textbook, inverse trigonometric functions are denoted using sine minus 1 and so on. So, for example, let's start with sine. How we proceed? We restrict x to the values between minus pi over 2 and pi over 2. Then the function y equals to sine x, we have pi over 2 minus pi over 2 minus 1, 1. Then the function sine x becomes strictly monotone. Hence, it has an inverse. So the inverse function is denoted by sine minus 1 y. So it is defined on the interval of the segment minus 1, 1. Or another way, more traditional, and which is used in your lecture notes, is arcsine. These are different notations, and I would say this one becomes more and more popular abroad, around the world. But I hope this will still be preserved. But sorry? Yeah, there's a thing, but yeah, different textbooks, that's all. Yeah, you should be ready to both of them. Yeah, okay. So what's about derivative? Okay, since in your lecture notes arcsine is used, I'll start to use arcsine. Arcsine is 1 over square root of 1 minus x squared, and here x is an interval. So you see that arcsine is defined on the segment, but it's differentiable on an open interval, right? So arcsine is defined is differentiable not at every point of its domain. It is not differentiable at the ends. Okay, so how we proceed? Yeah, we may use again x is arcsine y, that is inverse function to sine y is sine x, right? So we proceed then arcsine y prime equals to 1 over sine x prime, that is 1 over cosine x, and then we need to express cosine x in terms of sine x, more precisely in terms of y. We need to express our result in terms of y. Y is equal to sine x. And we observe that cosine x, cosine squared plus sine squared is 1, right? So cosine is generally plus or minus square root of, so in general cosine x is plus or minus square root of 1 minus sine squared x, right? But recall that x, which we have in the equality x equals to arcsine y, how it was defined? Only for x between minus pi over 2 and pi over 2. And if x is between minus pi over 2 and pi over 2, then cosine x is not negative, right? Hence, we may choose only sine plus. So, there is 1 over square root of 1 minus sine squared x. And sine x is y. And that is how we obtain the result. Analogously, we can proceed for other inverse trigonometric functions. Let's say arc cosine x. Again, here we observe that for the cosine we have similar graph, but the function is strictly decreasing. Why arcsine minus 1 was? Because, you see, derivative of sine is equal to 0 for the boundary points. Sine prime is cosine, right? At x equals to pi over 2, cosine equals to 0, right? So the derivative is 0, and you see the restriction, prime not equals to 0. To have differentiability, to have the differentiability, we need to have non-zero derivative. And sine x derivative at pi over 2 is 0. That is why we should exclude x equals to pi over 2 or y equals to 1. And analogously for minus 1. I hope I answered. We have a break. Okay? Okay, let's continue. So, still, oops, I don't understand if Masoud Wahid is satisfied by my answer or not. Okay. So, how to proceed with arc cosine? Yeah, okay, there is an answer from him. Good. So, for arc cosine, we can proceed as follows. Yeah, there is an easy identity, namely arc sine x plus arc cosine x equals to pi over 2. The reason is just, again, in the same formula for sine pi over 2 minus x and cosine x. So, and from that identity, we deduce the formula immediately, right? Or another option is again to proceed by the inverse function theorem. Okay. So, next is arc tan, the inverse function tan. Here no restrictions. Why? Because, look, we can proceed as follows now. We can consider the function tan x for x between minus pi over 2 and pi over 2. The graph is as follows. So, pi over 2 and minus pi over 2. All right, so, and we proceed like that. That is graph of y equals to tan x, right? So, this is strictly increasing function on an interval. So, derivative is never 0, hence it satisfies all conditions of our theorem, and we can proceed like in a standard way, right? So, x is tan y is equivalent to y is tan x. X is arc tan y is tan x for x in interval minus pi over 2, pi over 2. So, arc tan y prime is equal to 1 over tan x prime, that is 1 over derivative of tan according to 10th line is 1 over cosine squared x, and that is precisely cosine squared x. Now we need to express it in terms of y, right? And we observe that, okay, so tan squared x plus 1 is 1 over cosine squared x. Using that formula, we can write as 1 over 1 plus tan squared x, and that is precisely 1 over 1 plus y squared as we want. For 15th, arc cotan x prime equals to minus 1 over 1 plus x squared. Again, we can use similar identity arc tan x plus arc cotan x equals to pi over 2 for arbitrary x. So here the identity is valid for x in the interval, in the segment from minus 1 to 1, and here for arbitrary x. Okay? Okay, now more derivatives are related to hyperbolic functions and inverse hyperbolic functions. Okay, let me draw a picture. Recall the definition, let's just say. So, y is sine hyperbolic x. Let's consider that function. And that is, oh, sorry. In English, we use this notation, right? Yeah, sine hyperbolic. Sorry, I forget. Okay, sine hyperbolic. So that is e to the power x minus e to the power minus x over 2. What is the derivative? Okay, we may proceed. So sine hyperbolic x prime equals to 1/2 e to the power x prime minus e to the power minus x prime. We use chain rule here, so 1/2 e to the power x minus e to the power minus x times minus x prime, and it gives e to the power x plus e to the power minus x over 2, what is cosine hyperbolic x. So, okay, maybe I'll erase theorem about inverse function. We used it so many times. So that is formula 16. Sine hyperbolic x is equal to prime is cosine hyperbolic x. Similarly, we can proceed in inverse direction, right? Differentiating, and it gives immediately cosine hyperbolic x is sine hyperbolic x. So you see there is a difference between lines 8 and 9 and 16, 17. For hyperbolic, no minus for usual functions. But for tan and cotan, it's same. So 18th tan hyperbolic prime is 1 over cosine hyperbolic squared x, or seconds hyperbolic squared x. And cotan hyperbolic is minus 1 over sine hyperbolic squared, or minus cosecants hyperbolic squared x. Okay. I think I can omit the proofs because they're quite similar. But what is more interesting is for the inverse function. So for the inverse function, what is the inverse function? Okay, we can write just by sine hyperbolic minus 1. And in fact, the function is defined everywhere, no restrictions. There is another notation, not so, but I'm not sure if it is used even. Okay, I will not use it. So sine hyperbolic minus 1, and in fact it's quite different from the inverse function to sine, in the sense that we can find explicitly the formula for this sine hyperbolic minus 1, and this formula is quite useful for integration, for example. So let us compute what is this inverse. So look, we can rewrite our equality as e to the power x, e to the power 2x minus 1 equals to 0. Yeah, that is, I wrote that equality. So multiply by 2e to the power x. Multiply by 2e to the power x. And we obtain that equality. So, and now if we'll denote e to the power x as t, then we have t squared minus 2yt minus 1 equals to 0. So this quadratic equation we can solve explicitly, right? So t has two roots. We can compute them by the formula y plus minus square root of y squared plus 1. But remember that this t should be a value of exponent, hence it should be positive for sure, right? And if we take here minus, in modulus, square root of y squared plus 1 is greater than y. Hence, taking minus, we'll obtain negative t, which cannot be taken as a value of e to the power x, right? So it means that we deduce that e to the power x equals to y plus square root of y squared plus 1. And hence x is logarithm y plus square root of y squared plus 1. That is precisely explicit formula for the inverse function. Explicit formula for the inverse function to sine hyperbolic. Nevertheless, we can also proceed with the derivative of such a function, right? So maybe also I'll proceed with cosine hyperbolic. So for cosine hyperbolic, we let me write it down. What is about cosine hyperbolic? Y is cosine hyperbolic x, that is e to the power x plus e to the power minus x over 2, right? So here, if this is not a one-to-one function. In fact, its graph is like that. So we have here 1, that is y equals to cosine hyperbolic x. It's like that. So this is not one-to-one, but for x non-negative, it is one-to-one. So For non-negative x's, we have 1 to 1, strictly monotone. So we can find an inverse. So what is the inverse? X is cosine hyperbolic minus 1y. Let us again compute explicitly what is the formula. So if I rewrite it like before, e to the power 2x minus 2y e to the power x plus 1 equals to 0 now. Again, we denote t equals e to the power 2x, e to the power x, sorry. We have t squared minus 2yt plus 1 equals to 0. T has two values, and y plus or minus square root of y squared minus 1 now, right? And you see, now we cannot proceed in the same way as before because, modulo of this guy is smaller than modulo of y. It means both are positive, for y is positive, right? Hence, how we can proceed? We observe that e to the power x is t, right? And x is non-negative. Hence, what is about t? T is greater or equal than 1, right? So the restriction now should be t greater or equal than 1. And look, if I write y minus square root of y squared minus 1, I can write it like that. No. So I can multiply by y plus, and we obtain y squared minus 1. So you see, I multiply it, and we obtain this, right? And there is 1 over y plus square root of y squared minus 1. So, and you see what is what it means. Look at the picture as a whole picture, right? So you see, we have such a graph, y equals to cosine x. Now I want to solve that equation, right? To find x. It should have two solutions because of those two possibilities, right? One of them is smaller, another is greater. And we should choose which one? Which is greater, right? Because we want to have this version. And from this equality, you see, they are related by 1 over. Hence, we should choose just plus if we want to have our version of the inverse function for non-negative x. So it means that I can, once again, that is t e to the power x, so we have logarithm y plus square root of y squared minus 1. Again, y is, here y is greater or equal than 1 by the definition. Because y is cosine hyperbolic means y greater or equal than 1. So that is the domain of our cosine hyperbolic minus 1. So now let us compute derivatives of those functions. So let's say sine hyperbolic minus 1 y prime by the inverse function. This is 1 over sine hyperbolic x prime, that is 1 over cosine hyperbolic x. And now we should express our cosine hyperbolic in terms of y, right? And you see what is the relation between cosine hyperbolic and sine hyperbolic. An analogous of the general trigonometric identity is cosine hyperbolic squared x minus sine hyperbolic squared x equals to 1. So from this equality, what is cosine hyperbolic? Is square root of 1 plus sine hyperbolic squared, right? And sine hyperbolic x is y. That is, so the line 20th, the inverse hyperbolic functions. So, okay, what we obtained, sine hyperbolic x, sine hyperbolic minus 1x prime is 1 over square root of 1 plus x squared. No restrictions because it's defined everywhere. For the cosine hyperbolic, it's quite analogous. So we proceed in a similar way. So 1 over cosine hyperbolic x prime is 1 over sine hyperbolic x. Once again, we may compute using the general hyperbolic identity, that is square root of cosine hyperbolic squared x minus 1. And why we choose plus here? Because of the definition. So for cosine hyperbolic, we have only positive version. Only positive version is taken. So, and it gives 1 over square root of y squared minus 1. So we obtain 21st cosine hyperbolic inverse is 1 over square root of x squared minus 1. So here the restriction x greater than 1. X greater than 1. And of course we can proceed in a similar way with tan hyperbolic and cotan hyperbolic. And yeah, in fact, all those formulas after 19 are not obligatory. I mean, you don't need to remember them, and in fact, they're useful, but I would say not necessary to remember. So, but as a good exercise to be able to use those rules for derivatives, it's a good idea to consider them. So let's now consider tan hyperbolic. Minus 1, right? So let's compute tan hyperbolic minus 1 y. That is 1 over tan hyperbolic x prime. And tan hyperbolic gives us 1 over cosine hyperbolic, so we have cosine hyperbolic squared x. Now we need to compute it in terms of y. So it means we should find an analog of trigonometric identity for recall how we computed arctan. We choose an analog, we choose an identity tan squared x plus 1 is 1 over cosine squared x, right? This, right? So what is for tan hyperbolic? Let's think tan hyperbolic. If we, that is sine squared hyperbolic over cosine squared hyperbolic, and it means that if I write 1 minus, that is 1 over cosine hyperbolic squared x, because of the main hyperbolic identity. Okay, I'll write it once again. Main hyperbolic identity. So it means here we have 1 over 1 minus tan hyperbolic squared x, and that is 1 over 1 minus y squared. So we obtain a formula for tan hyperbolic inverse, which is 1 over 1 minus y squared. Oh, sorry, x squared. X squared. That is for the inverse to tan hyperbolic. Analogously, we can proceed with cotan hyperbolic. Okay, so let us compute cotan hyperbolic. Tan hyperbolic minus 1 y is 1 over cotan hyperbolic prime. Cotan hyperbolic is minus sine hyperbolic squared x, and once again we should compute. So analogously we can write down now cotan hyperbolic squared x minus 1 equals to 1 over sine hyperbolic squared x. So it gives, it gives what it gives, minus same expression. 1 over 1 minus y squared. So same expression. 23rd cotan hyperbolic minus 1 over 1 minus x squared. Okay? In fact, if I have a look at another textbook, Then there is a huge amount of formulas here for derivatives. Maybe, yeah. I can write them down for fun and we can check some of them. Okay, where is it? Just trigonometric. Oh, by the way, also, yeah, there are inverse seconds and so on. Okay, maybe I can write also, yeah, 24th. Yeah, but then I should write, okay, seconds minus 1 u is 1 over modulo u square root of y squared minus 1, okay, maybe x squared minus 1, yeah, also 25th coseconds minus 1x is similar with minus 1 modulo x greater than 1. Where are inverse hyperbolic functions? I can't find inverse hyperbolic. Ah, it's another chapter. For many years I forget where is it. It was hyperbolic functions. Yeah. Yeah. Yes, inverse hyperbolic. Yeah, derivatives of inverse hyperbolic also there are. Also there is a table for 26 hyperbolic we wrote. Okay, so yeah, seconds hyperbolic minus 1 is minus 1 over x square root of 1 minus x squared. Yeah, here x from 0, 1, 27 coseconds hyperbolic minus 1 is minus 1 over modulo x square root of 1 plus x squared, x not equals to 0. Yeah, here, yeah, I wrote, okay, yeah. So these are formulas for the inverse non-standard, I mean, seconds, coseconds, and hyperbolic seconds and coseconds. Yeah, of course, we can proceed, let's say, yeah, what is for 26, line 26. So y is seconds hyperbolic, better to say x is seconds hyperbolic minus 1y, y is seconds hyperbolic x, so seconds hyperbolic minus 1y prime, 1 over seconds hyperbolic x prime. Oh, by the way, we didn't compute seconds hyperbolic. Okay, let's compute. Seconds hyperbolic prime is 1 over cosine hyperbolic x prime, that is minus sine hyperbolic x over cosine hyperbolic squared x. So we substitute minus cosine hyperbolic squared over sine hyperbolic x. Now we should compute it in terms of seconds hyperbolic, that is minus 1 over seconds hyperbolic squared x. Wait. 1 over cosine hyperbolic. Sine hyperbolic over cosine hyperbolic. Yeah, and sine hyperbolic square root of. Yeah. Now, what is sine hyperbolic? Times, yeah, sine hyperbolic x is square root of cosine hyperbolic squared minus 1. There is I may put cosine hyperbolic x outside square root and 1 over cosine hyperbolic squared x, and it gives 1 over seconds hyperbolic times square root of 1 minus seconds hyperbolic squared. Yes, so that is the representation for sine hyperbolic. Sine seconds hyperbolic x square root of 1 minus seconds hyperbolic squared x. Yeah, we cancel it, and finally we obtain minus 1 over y square root of 1 minus y squared, for y is positive, right? Yeah, for y is positive. That is how we can check one of them, right? Analogously, you can proceed with other formulas, and yeah, and I would say these are tables from textbooks, from other textbooks, but I would say I never used any of them, never. Yeah, so those little bit crazy formulas, you don't need to try to remember formulas starting from 20th. Yeah. Okay, yeah, so it seems, yeah, we can stop now. Thank you.